Merci beaucoup pour l'organisateur. Thank you, Hervé and Muriel, for inviting me. And well, I'm going to give a very wide overview about meteorites, but also about bodies from which the meteorites are coming from. And I hope will be, in general, useful. As the rest of the talks, this will be available as a PDF file. So you will realize that there is some explanations of every slide with the intention of going through the matter, the main ideas that I'm going to explain. Probably some of the slides I'm not going in deep detail about everything is in the slide, but of course you are very welcome at the very end or during the beer time or whatever to ask me about any of these contents, and I'm happy to, of course, show you on the computer again and explain the things, because I want you to retain more or less the essence. And you will see I will say my focus here is that you really realize how important are meteorites in our knowledge, not only of the formation of the solar system, formation of the planets, if not in our own presence in the cosmos. So I'm trying to link meteorites with astrobiology. Just to put you in context, I will just show you a very fast slide. This is the institute I belong. It's the Institute of Space Sciences in Barcelona. It's an excellent institute of the Upper Research Council in Catalonia. That I have several PhD students, some already doctorate, with some of the results of these doctorates are shown in this slide, so it's also their fault. And well, our main group lines are concerning, for example, the recovery and characterization of new meteorites. We have recover and characterize some of the last Spanish falls, but also falls in South America, and where we are working also on the characterization of new finds. At the same time, we are the only institute in Spain that has expertise in NASA Antarctic meteorites. We are an international repository of NASA Antarctic meteorites that will provide many of these fascinating results I will explain you later. And then we are working with a special interest in aqueous alteration, in the action of water in different environments. For sure in asteroids and bodies that we can call transitional, mid-asteroid, mid-comet, and also in planetary bodies like, for example, Mars or other places. And we are also performing laboratory experiments to gain insight about the different processes taking place in these bodies. Not only aqueous alteration, we are also dealing with collisional compaction, shock affecting and transforming the minerals. And we are also working on issues related with impact hazard, the influence of all this evolutionary track of the small bodies of the solar system. And finally, we are also dealing with the fireball, Spanish fireball network that we have been running for more than 20 years now. So just as an outline of the talk, I will explain, I will go about these ideas that Professor Maynet was presenting this morning. Stars, I will introduce stars as source of chemical elements in the context of the local environment in which the solar system was formed. I will talk a little bit about young stars and protoplanetary disks, focusing in our own protoplanetary disk. And I will describe a little bit the violent origin of planetesimals, the creation, disruption of building blocks, the gradients of temperature that were at work in the protoplanetary disk. This was the first part of the chemical segregation of the elements through the disk that was having a very significant influence on the bodies that were growing from these materials as a function of the heliocentric distance. Then I will go all over the different types of meteorites and their origin. As I said, I'm going over a very wide overview, so I will jump in some parts, but and of course I will concentrate in the key chondrites that are particularly I will describe some chondrite groups and some discussion about the reflectance properties, reflectance capability of these materials to reflect the light of the sun of another star is a key way to understand what is the mineralogy, what is the composition of the asteroids and comets that we are looking usually from very far away. So it's very important to understand what are the reflectance properties. Then I will go describing a little bit about the components of chondrites, and finally, hopefully, I'm able to go over a quick overview of the differentiated meteorites, chondrites, to talk a little bit about the Moon, Vesta, Mars, and other bodies. Well, you know, the most interesting thing about the origin of the chemical elements, as was previously described, we have this primordial nucleosynthesis that was coming out from the Big Bang. Originally, all the universe was hydrogen and helium, and the rest, this lithium, beryllium, and boron, were produced by spallation. So at the very beginning was not possible to find planets like the Earth or beings like ourselves. In this context, the astrobiology is the study of life in the universe, just concentrated perhaps in three parts: the origins, distribution, and evolution of life, structures and processes related to life in the universe, and explicitly the destiny of life. Well, in this graph, where we have the atomic number in here, we cannot see the pointer? Ah, okay. 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 The atomic number, and this is the logarithm in base 10 of the abundance of the elements. So you can see that the hydrogen and helium are the more abundant elements at our present time, and these are the elements produced in this Big Bang nucleosynthesis. I'm not going in full detail about this because it was already explained this morning. So in general, after this almost 3,000 millions of years of evolution since the Big Bang, we have the different galaxies are full of molecular clouds with masses of thousands, 10 of thousands solar masses, and these huge clouds are subjected to gravitational force, so locally, as was explained before, are able to condense and produce this kind of thing we observe, for example, in the Orion Nebula. This is a protoplanetary disk edge on, where we can see the visible and the infrared image seen by Hubble. where here is some red, but here is clearly the protosun just born from the material that has been collapsing. These kind of objects are also typically observed in these environments in which you see a stellar cluster born from the molecular. The border of this border is also produced by the radiation pressure of the stars that are young stars just born from the cloud. So they are producing a front that is cleaning the gas all around them, okay? And of course the protostars are having this kind of shapes. You can see, in fact, we cannot see the protostar, usually it's too small, but we see the jets produced by this bipolar ejection of gas that is falling against the star. Then, because of the geometry, the gas is released in the north and south direction, and this typically observed by also radio telescopes because they are masers that are releasing hydrogen at very high velocity and going through the media. So this is these are the first theoretical approaches describing this kind of bipolar outflows, and these objects are called Herbig-Haro objects. In these molecular clouds, it's particularly important that you have the stellar nucleosynthesis. So the molecular clouds are not essentially hydrogen, helium, and few elements more. If not, they contain this pleiade of other elements that in fact are consequence of the chemical evolution of the galaxy, of the stars forming the galaxy. How many stars have been destroyed or just thrown away through the winds to the interstellar medium have been enriched, enriched over time the composition of these molecular clouds. In fact, we know that they are stellar components. If we study the first materials that we can study by just looking at the interior of the meteorites, we see that it was a positive contribution of supernovae and red giants to the materials that were at the very beginning in the solar nebula, that were just forming the first materials. So the evidence for materials from another stars comes mainly from presolar or stellar grains. I don't like the term presolar because it could be contemporary to the solar nebula as well. Radioisotopes that can be in the components of these meteorites or trapped in the matrix, in the fine-grained materials forming these meteorites, and the isotopic anomalies that are could be from different sources as well. A particular point are the sources of radionuclides. This is a key point. You see that aluminium 26, calcium 41, manganese 53, and iron 60. This is the parent and the daughter that we can find nowadays in meteorites, and these are the half-life in millions of years, and these are the stellar sources. Usually in the literature has been invoked aluminium 26 and iron 60 from supernovae, but we were proposing massive or intermediate mass asymptotic giant branch stars a source of these key elements. And these are key elements from the point of view that have been considered to be the source of heat, of the primordial heat that was when a planetary embryo is formed, is heating the interior and is melting the materials to go away with the chemical segregation, you know, in different phases. So we propose that, in fact, we realized that 6.5 solar masses AGB star with a solar metallicity could have played an important role in the early solar system. There is obviously evidence, from my point of view, that the Sun was not alone when formed, if not probably was in the interior of a stellar association. We think so because some of these radionuclides incorporated alive into these materials. So necessarily you should have a source of these live nuclides really close by the solar nebula at the time that shorter at that time were condensed to form the solid phases. You know, it's the way in that they incorporate from the vapor phase to condensate to form the first minerals. Okay, so the good thing of the model we publish in Meteorites and Planetary Science is that by comparing the short-life nuclides abundances in primitive meteorites, the evidence we have in the literature, with the pattern that we model from a 6.5 solar masses star, our model was matching the abundances, which is vibrating, the abundances of aluminium 26, calcium 41, iron 60, and palladium 107 that are inferred to be in the solar nebula. What we did is a dilution factor of 1 part of AGB material per 300 parts of original solar nebula material. So with the right mixing, you can get the right ratios for these short-life nuclides. At the same time, this model is able not overproduce 53 manganese, as supernovae models do, and only marginally affect isotopic ratios of another stable elements. It's just one idea that we can really manage to have some modeling, astrophysical modeling, try to link the chemical composition of primordial meteorites, chondrites, with the composition that was probably affected by nearby stars at the time of formation of our planetary system. As you can imagine that at the very beginning you have, this will be just a sectional cut of the protoplanetary disk, the star in the center, and then you have, this is the midplane, and as you can imagine there is strong radiation of the order of 5-6 orders of magnitude. Current radiation of the Sun was the amount of ultraviolet radiation, for example, of the proto-Sun. We know that for the study of another young stars, like T Tauri stars. So close by the proto-Sun, you have really extreme temperatures and very high radiation flux. But there is, of course, some shield because of the materials that are in the interior. So in the outer midplane, and particularly when you are going far away from the outer exterior, you have some shielding, and then the temperature can be dropping over time. Of course, depending of the circumstances in which and the time you are studying the different parts and the different locations in here, you can get different chemistry. And of course, I will just go over. As a consequence of the different distance from the sun, you have here the temperature at epoch of the dust settling of the materials. The idea is that you have originally a solar gas, a star that is collapsing, and the star really plays a role, because in the moment that the ignition takes place, there is a radiation pressure working and cleaning the fog, cleaning all the gas that is all over these materials, and as a consequence the temperature drops abruptly, and then some of the components of the vapor are condensing into nanometric particles. The silicates, the metal grains are just getting out from all these circumstances. This is a model by Del Sem in 2000, in which you see that there is a temperature gradient. Closer to the sun, you have temperatures about 2000 Kelvin, and then you can get down at the distance, the current distance of Saturn or Jupiter, and you have here the condensation of volatile snows, ices, and condensation of organic matter more or less at the outer edge of the current main belt. But depending on the distance, you have less temperature far away, and then it allows the condensation of phases that are of low temperature. Okay? As a consequence, you have the formation of the planetesimals, the so-called planetesimals, solid rocks in the first part, the inner part of the disk. Depending on how close is from the sun, you have different minerals. If they are more close to the sun, in more reduced, that means in absence of oxygen, then in relative absence of oxygen, you have more enstatite-like silicates, and when they are incorporating more oxygen, you have more oxidized conditions. That will be in this part where the carbonaceous chondrites were formed. And then in this outer part of the disk, you have what we call cometesimals, that the first blocks forming comets, because contain some kind of mixture between fine-grained silicates, let's say 1/3 of each, more or less, organic matter, and ices. Some mixing of these materials as well. This is also the present location. Any of these planets were formed at that time. It's just for your more or less showing the positions of the main minerals, and you can see here that the olivine, pyroxene were formed at the location where the terrestrial planets are nowadays. Iron also, thoylite, the sulfides in here, and water and ammonia, methane were very far away because the temperature, the condensation temperature are much smaller. So a sectional cut will show you in the outer part of the disk more than 10 astronomical units the formation of probably some subnebula, some accretion of gas that was giving the giant planets, together with a huge amount of cometesimals that were also participating in the growth of these outer disk bodies. In the inner part, you have, this is the snow line. It's the place where the solar radiation is not allowing the ice to be in liquid phase. But the thing is that you have in the, more or less, the scenario can be, you know, applied to different environments, having into account and how, from the point of view of time, you know, this have been evolved. And of course, depends of the stellar flux and many other parameters that are evolving over time. It's just a general overview, of course. So, of course, we should not forget either that all the materials that are condensing and are forming these chondritic bodies are also suffering the decaying in the protoplanetary disk, so they are going inwards and they can be heated or fragmented over time, so they incorporate, for example, part of this carbon or oxygen to the vapor phase. So this is a highly dynamic system. It's not at all static. This has the feeling that you get that everything should be, but it's not. Really, these materials are forming over here and then they are just falling, and even some of them are evaporated. No? In fact, some of the models that are explaining the young stars, there is an invoked model that is the falling evaporating bodies. It means that when you observe a young star, you can have chance to see absorption lines produced by the materials that are going against the star. They are falling. There is a continuous disruption of very fragile materials. I should say, I'm not explaining it in detail, but we demonstrated using some laboratory studies with Professor Jürgen Blum. They are, for example, some papers in 2006 in the Astrophysical Journal, where we demonstrate that the first materials, the first building blocks of planetesimals were really having very high porosity. So they were very fragile, and then in those scenarios everything was really weak and fragmenting and recycling all over the solar system. And as you can imagine, and we can stay here for hours, but if you have materials here that are fragile and are colliding with each other and are falling against the protoplanetary disk until reaching the star, you have a lot of recycling of materials that are going to the vapor phase and going back and so on. And some of these materials that are evaporating, because of the high luminosity, the radiation pressure, some of them are going back to this outer part of the disk. Particularly, particles that are less than 10 microns can be perfectly flow up to the location formation of comets. Again, as we demonstrate, I will show you in the Stardust mission to Comet 67P. So, as a brief introduction, the protoplanetary disk cleanup, these are some of the phases that we go in just as a summary of what I was explaining. In about 10 million of years, you have the evolution of the protoplanetary disk, initially with some gas between these kind of rings form, and then from when the star starts to generate so much energy, part of the gas is released to outer space, and then you start to form these rings with the materials that have been condensing from the vapor phase. And finally, after few tens of millions of years, you have the planetary embryos just surrounding the star. One of the most amazing things of studying carbonaceous chondrites, like for example Orgale, is that these meteorites that have been heavily aqueously altered, if you compare, this is a logarithmic scale of the CI. The C is from carbonaceous group, and CI is from Ibuna, that Orgale belongs to this Ibuna group of carbonaceous chondrites, and you compare the composition of these CIs with the composition of the solar photosphere, you see that there is a really good match for most of the elements. So this rock that some of the people that was able to recover this Orgale meteorite was cutting with knives is really representative of the composition of the sun itself. How is that possible? Because it's really challenging from the point of view that most of the meteorites that are arriving the Earth are ordinary chondrites and are rocks and are having some similar composition with the sun, but not to this much. And the reason for that is that these really fragile, highly porous materials contains minerals that have incorporated in their bounds, you know, these volatile phases from which they form. That's one of the most amazing things of carbonaceous chondrites. They can retain the stellar environment from which they were born. Again, if you look again to this graph and you look at the elements that are involved in the formation of living beings, you know, there is a clear correlation. There are some elements that are participating, are quite abundant in these materials. And if we look particularly to the elements that are in the Earth's crust, it's quite nice to compare that the rock forming elements are really in some abundances that are very close to the elements that are producing life. Somehow, perhaps this is telling us that the Earth is a place where the elements forming rocks are not so far from the elements that are forming life. So perhaps this kind of chemistry can be reproduced all over different places like in Earth. In this periodic table, you have the abundance represented by different size. Okay, you see that again the hydrogen, carbon, nitrogen, oxygen are dominant in Earth crust. So somehow the Earth could have the conditions and the abundances to produce life. In our group, we are looking for the most primitive chondrites. We are looking for highly unequilibrated chondrites. It means that these meteorites haven't been, or at least to a very big extent, not aqueous alteration, no thermal metamorphism. In such a way, the different components of these chondrites that probably remind you some marbles, okay? This is a thin section, and you can see a iron oxide-rich chondrule, iron oxide poor chondrule, more olivine-rich, and many other components, fine-grained fragments of chondrules or calcium aluminum rich inclusions and so on. But these are highly unequilibrated. So in some extent it's like just taking you know a spoon of the materials that were forming the disk were almost not affected by the compaction or the incorporation of water that was producing in other chondrites stream aqueously alteration. These are the most important classes of carbonaceous chondrites, of chondrites, the ordinary chondrites, the enstatite chondrites, the carbonaceous, some anomalous, and in each one of these classes you have the groups, ordinary, enstatite, carbonaceous, and anomalous. Each one of these groups have a specific elemental chemistry that is able to distinguish from each other. In some groups, these are called petrologic types, and the most pristine meteorites that have not suffered to very deep extent thermal metamorphism, neither aqueous alteration, will be the petrologic type 3. So if you hear about Axfer 094 or Alan Hill 77307, you will see that, for example, this Alan Hill 77307 is a very pristine meteorite from the CO. The O comes from Ornans, and this has the petrologic type 3. That means that is pristine, just in a very simple way. Those meteorites that have suffered aqueous alteration can go to petrologic type 2, or if the aqueous alteration is extreme, petrologic type 1. Okay? And if in case of thermal metamorphism, that could mean that these materials have been cooked in the interior of a larger object, larger asteroid, for example, these are going to petrologic type 4, 5, 6, and that most of the ordinary chondrites are having these 4, 5, 6 petrologic types. That it means, in a very simplistic way, that they are probably formed at different depths in their parent asteroids. Okay? Well, the main minerals in chondrites, the main rock-forming minerals, you see that in the chondrites we observe the chondrules, the calcium aluminium rich inclusions, metal grains, and fine dust components. For the silicates, you can find the olivine, or in particular the primordial olivine is magnesium rich olivine, and this iron rich, the incorporation of iron depends also of the degree of heating of the material in the protoplanetary disk and in the interior of these bodies afterwards. Then you have the pyroxene and other minerals like enstatite, that is more common in the inner part of the disk because it has not so much oxygen in the structure. And then you have plagioclase and sulfides like thoylite or pyrrhotite as well. If we observe these materials using X-ray mappings and you give to the magnesium a red, to the calcium green, and aluminum blue color, then you end with this kind of images where you can see here a magnesium rich chondrule or fragment of a chondrule, violet calcium aluminum rich inclusion because it's a mixture between calcium aluminum, green plus blue. Okay, and you can see this kind of beautiful things. This is about 200 microns, and this is about 1 square millimeter. And you hear these ameboid olivine inclusions, the kind of aggregates. And these are observed in Axfer 094, that is one of the meteorites I have been working in. As this is a highly unequilibrated meteorite, all these phases are out of equilibrium with the matrix surrounding the materials. So they are representative of the materials at the very beginning from which these bodies were formed. The condules, some of the condules are rich in iron. In this backscatter, this microscope images, you can see when they contain more iron, they are brighter than when they lack of iron, but the iron could be as metal grains. So here we have a high FeO type condule and low FeO type condule. At the same time, we have, fortunately, some quite pristine ordinary chondrites. So we can go even over the first step in the formation of condules. And these kind of images can show you that a very big condule is formed by an aggregate where you can see magnesium-rich pieces, you know, because was not able to complete the chemical equilibration of the melt, you know. So this is telling us that in general condules are produced by heating of fine-grained materials, you know. You have these magnesium-rich silicates condensing from the vapor phase at really small sizes and then forming comets. These tiny things mixture with organics and ices doing things, but when they went inwards, the protoplanetary disk, they were forming aggregates, these IDPs things, that when they just got hit or heated by the irradiation were melt and stayed in melting state for hours or days in the nebula, perhaps also incorporating some materials at that point, you know, and when the time passed, this solidified, forming condules. And the term chondrite comes from condules that are the most abundant components of most of the chondrites. Okay, some chondrites lack of condules, but that's another issue. But in general, the term chondrite comes from this. So this is the evidence that the really tiny minerals that were forming were processed in the protoplanetary disk. So were producing from micron size to millimeter or centimeter scale components. Not only condules, you can have even more extreme processing that should be the calcium aluminum rich inclusions. These ones. You see here in Asphere 094, that is quite amazing. I shouldn't go far away than that. You see here that this kind of aggregate is following the same magnesium, calcium, aluminum path than I previously explained. So this is calcium aluminum rich particle, and you can see here kind of aggregate in the nearby the particle. What this means? That this was an aggregate, and this aggregate was going inwards and was, unfortunately for him, going too close to the sun, where all the volatile silicates, or not all, but a significant part, just vaporize. What remained? Oxides, calcium aluminum oxides. You know, that's a very important picture of what was going on. You have different stages of heating, of processing, thermal processing in the protoplanetary disk. How we know it? By studying the components of some of these really amazing, really preserved chondrites. And the amazing thing in this These are some of the most common minerals: spinel, melilite, hibonite, just for your general knowledge. But these calcium aluminum inclusions also retain a variety of isotopic anomalies in oxygen 16, aluminum 26, manganese 53, calcium 41, rubidium 87, that probably were inherited from incompletely homogenized materials. And this could have some idea that the environment in which these materials were formed was probably subjected to the incorporation of materials from nearby stars. You know, because in any of these, some of these meteorites have very specific formation times and are not identical. So perhaps in the future, if we are able to get more of these really pristine meteorites, we can go into the details how the abundances of these live nuclides were changing over time. It's a very fascinating possibility. When we compare, on the other hand, the composition, this is the abundance compared with the CIs. If all these groups, ordinary chondrites, CB chondrites, and CM chondrites, M from Miguel, B from Bigarano, that are the first meteorites of this class, of this group, excuse me. So if everything was comparable with the solar, solar is a little bit out, the CI, the composition of the Ibuna group of carbonaceous chondrites, then all this should be in this line. But the thing is not. Each of these groups have, as you can see here, a different pattern, a different slope. Some is not so like a straight line, of course, but you observe clearly differences. So it means that the materials forming the different chondrite groups suffer different degrees of thermal processing. Okay, so it seems that it seems that all these models about protoplanetary disks that were proposing formation of rings, that some of these groups perhaps are representative of different distance to the Sun. Well, we are observing these kind of things. We are observing that in other stars, like for example HL Tauri, just using the Atacama Large Millimeter Array, ALMA, we observe this kind of gradational differences. So we expect that the composition of each one of these rings should be different somehow, and is really what we are observing. But yes, we have this amount of new data about meteorites, but there is a big challenge. We need to really understand each one of these meteorites from which body is coming. The chondrites represent a dominant part of the main belt population, particularly the smallest bodies, but still our collections of meteorites are highly biased. At the present time we are receiving meteorite groups that probably are not all the compositions that are likely in the main belt, for example. At the same time, we have also large bodies, I will discuss in the achondritic part, but we have really a challenge puzzle, in the sense that we know afterwards we made this modeling on how these asteroids have been affected by collisions over time, and how they are compacted is what we were modeling in this astrophysical journal paper. What we conclude is that most of these chondritic asteroids have suffered a huge collision rates, to the extent that most of these bodies probably were suffering really huge impacts that were destroying, in many cases, just able to disrupt the asteroids. Or if it's not the case, you have really regolith, just collisional process material with a depth of kilometers. So you are not observing really the body, if not just the amount of processed material that is over the top of this regolithic material. It's not surprising, because also we know that in the moon we have regions covered by mega regolith, huge blocks produced by these collisions over the eons. These processes are called impact gardening. This gardening, in which you have the ejecta that is excavated by the impact, is coming back in some cases to the surface, and then is covering the surface over time, and of course affecting the reflective conditions. At the same time, you have huge impacts, or huge impactors, but you have also small meteorite projectiles plus really radiative energetic radiation going through the surface of the bodies, and this is also producing this comminution. So over time you have that the materials on the surface are affected by this micrometeoritic bombardment, and also the solar wind and cosmic rays are affecting the surfaces, and this is really producing that the material is being fragmented over time to size very small. So this is the comminution process that is observed, for example, in lunar regolith. When we look, for example, to space missions like EROS or HAYABUSA, EROS asteroid and ITOKAWA asteroid, you see that really the surface of these bodies are covered by boulders, big blocks, or small pebbles, even just micrometer size dust that are incorporated over the asteroid over time. And as you can imagine, this is really hiding what is in depth. It's really challenging, because over time these bodies could have been in a region where have suffered thousands, millions of impacts, and then have been covering the surface of materials that are not necessarily the composition of these asteroids. So it's kind of mixing, you know, and that's why it's a challenge, and we need to program the exploration of other bodies. This slide is a very beautiful slide from Francesca De Meo. It's a PhD thesis in which you see, as a function of the heliocentric distance and the present location of the planets, you see that this is the reflectance spectra from 0.4 microns up to about 1 micron. Okay, and you see how different are the materials depending on the different reflectance classes. So, just for not getting you lost, each let's say the asteroids that are reflecting in a very similar way the light of the sun are identified as a class. Okay, the V class is a type of asteroids, you know, that is related with one class of meteorites that is associated with Vesta and have specific absorption bands that are characteristic of differentiated meteorites. Ordinary chondrites that are similar to these S-class asteroids, you know. So you can have some idea of how this behaves. We are just matching asteroids by their similar reflectance. We have not chemical information other than the reflectance of light. And then we make these matches. Of course, when you go out, you see these almost flat behaviors, and when we are jumping to the trans-Neptunian region, you start to see methane, water bands that are consequence of less processed surfaces. Okay, so in the case of the ordinary chondrites, we can see here that can be distributed. This is the weight percent of iron oxide and the weight percent of iron in form of metal grains plus troilite. You see, and you see that they are specific groups. The H chondrites, that means height in metal and troilite in reduced form, the L chondrites that are more oxidized, and the LL chondrites that are in this part. In here you will have the carbonaceous chondrites. I will explain later. This is the spectral reflectance characteristic spectrum for asteroid Eros, for example. Okay, well, you can see the olivine and pyroxene sometime bands that are characteristics of this. The plausible origin that has been proposed, at least, of the L group is the Gefion asteroid family that was born during a catastrophic collision about 485 millions of years ago. This family is also next to the Phi-2 resonance, that is the way as the fragments of these collisions could reach the Earth, just by gravitational perturbations. You can see in here the semi-major axis. Each one of these points are asteroids. Okay, this is the inclination, and this is the Gefion family in detail here magnified. These different red pieces are parts of the progenitor. You know, Gefion was bigger but was suffering a very huge collision and fragmented in many pieces, and each one of these pieces is having very similar reflectance spectra, not necessarily identical but quite similar. In here you can see, for example, the location of Ceres as well. This is from in this specific part. This is eccentricity and this is inclination. And here is again the same family, the Gefion family, that is more or less in the middle of this distribution. Well, by doing what Japanese Space Agency was doing on Hayabusa, we really learned how these objects were formed. And as you can imagine, this asteroid is a nice example of what we call a rubble pile, a body that was initially having perhaps tens of kilometers, hundreds of kilometers in size, but that was just impacted by a body probably in the same size or little less than that, and then as a consequence of this huge collision was scattered into pieces, and some of them were going back to form the present asteroid. You know? ITOKAWA is covered by fine-grained regolith rocks and boulders that are the product of this collisional gardening, and also have suffered space weathering, aging by cosmic irradiation, solar wind, and the mineralogy is associated with the chondrites, ordinary chondrites from the group LL, low metal, low ACO. Okay, if we compare the composition of the ordinary chondrites, you see here the different groups, and ITOKAWA, this is the facite and phyalite composition in modal percent. You see here that ITOKAWA is here, so it's clearly in the LL group. You know, this doesn't mean necessarily that the LL chondrites are coming from ITOKAWA, because can be in fact that you have a specific bodies that are having similar composition. But as you can see here, these highly equilibrated ITOKAWA particles are in this part that are matching very well the phyalitic composition of the silicates. We have been working in our laboratory at the Institute of Space Sciences of some of these regolith particles. You can see here one of them that is about 100 microns in the long axis. And we have been studying in particular the mechanical and the magnetic properties. And this is hopefully will be soon a forthcoming paper. The interesting thing that these particles have been on the surface of the asteroid ITOKAWA for thousands of millions of years and have been affected by collisions, by these space weathering processes, but the properties, the mechanical and magnetic properties, are not very different from the chondrites that have been less exposed to the interstellar or interplanetary space. This is from Osaka University, some kind of result of all this HAYABUSA mission, in which you have the evolution. You have a parent body of ITOKAWA larger than about 20 kilometers in size that was suffering this cataclysmic disruption. Then the fragments were reaccumulated, and this was happening about 1.4 gigayears ago, and then was some resurfacing, so mostly 8 million years ago, then going this body to a new secular resonance with Saturn that was bringing the body to the current orbit in which this was studied by HAYABUSA mission. This kind of body finally could have ending their days just colliding with the Earth or the terrestrial planets. So it's quite interesting to study these kind of materials. And as you know, we also had impacts, very recent ones, like Chelyabinsk. We have been also studying Chelyabinsk. Particularly, we are very interested in the high pressure phases that are produced by impacts. Some of the materials that are on the surface of the asteroid, when just is getting so high energy, and the shock waves that are crossing the material is just affecting completely some in the sense that is also contributing to thermal some thermal metamorphisms produced by shock, and this is also affecting the meteorite. They are producing melts all over the meteorite, cracks that are filled by the vapors during microseconds, you know, and are forming this kind of structures that you can see in here. Some structures, some fractures filled with shock-induced minerals that we can study using Raman spectrometers. Is what we have been doing, for example. In here you see that the olivine is transformed into meteorite. It's a high pressure polymorph of olivine. And in case, for example, you have also the incorporation as phosphorus is going easily from plagioclase or other components of the meteorite to the vapor phase in the interior of the meteorite because of the stress of the shock wave going through. Then you have the formation of this polymorph of meteorite that is having this trigonal structure in shock veins. We can characterize these materials using these Raman spectrometers, and also we are having the ALBA synchrotron really close our installation, so we can also use these in fractures. Okay, well, perhaps this is too dark, but so, well, basically here you have this axis is the heliocentric distance. This is 5 astronomical units. This is 2 astronomical units, and this is the percent of total population. And you see here the E, S, C, P, D. These are spectral classes of asteroids. And you see that the enstatite population is mostly in the inner part of the main belt. This is the location of the main belt. Here you have the S class of ordinary chondrite like asteroids, the C from carbonaceous, P from carbonaceous chondrites as well, and the D that is more some kind of pristine population, perhaps more transitional with comets, between asteroids and comets, something like that. As you can see, most of the really processed materials, enstatite-rich materials or ordinary chondrites, are in the inner part, and most of the asteroids that are less processed are in the outer part of the main belt, nowadays. So it's what we were expecting from this modeling. In case of carbonaceous chondrite, we have this Matilde, this kind of reflectance spectra with few absorption bands. Sometimes you have clear absorption bands, for example, from water, phyllosilicates, and other and oxides and carbonates. But in general, they lack of very deep features, except perhaps water bonds and so on. As I said, the carbonaceous chondrites, one of the most important things that they were able, in some cases, some groups contain until 10% in water and 4% carbon in mass. So they are rocks, but they are just retaining part of the volatiles from which they form. It's one of the most fascinating things of carbonaceous chondrites. And this is because part of this water was bonded in the minerals themselves. You know, you have water as phyllosilicates, from the silicates were transformed in phyllosilicates, from the iron phases were oxidized to produce hematite and other minerals, you know, that were born from in the interiors with the presence of water, and we can study all these things. We use these spectrometers in order just to deal with the behaviors. You have here this for part of a Molly Notices paper we published concerning from the ultraviolet to the near infrared, what was the behavior of some different groups of carbonaceous chondrites. We try to really use this data in order to understand if depending on the albedo or the different slopes and features that we observe, small features, we can help to characterize primitive carbonaceous asteroids. But one of the most interesting things in which we are now working is the aqueous alteration. We have been working particularly on the models that try to explain the alteration of the parent asteroid of the CM carbonaceous chondrites. I will give you some details in the next slides. And we have been now working in the new group. Well, it's not new, but we start to discover more in Antarctica of these CRs. That is extremely interesting because some of them are very pristine and contain clues of how water was incorporated into these materials. In the CM group, you have clear features from one meteorite to other meteorite from the same group, that some of these meteorites were coming from different depths in the parent asteroid, because you have different degrees of aqueous alteration for meteorites that are having similar composition, and then they are probably forming from a similar object. When we look at, for example, the famous Murchison meteorite, we deal with very interesting observations. For example, you have this condyle that is an iron-rich, as you can see here, olivine form condyle with the metal grains in the interior. And then you see here is the fine-grained materials that are surrounding the condyle. But if you look in detail to here, you see that this metal grain that was just in the border of the condyle has been corroded by water. And part of this corrosion is going inside the condyle, as you can see here. These form parts of a review paper we have just published in the Space Science Reviews this year, just 1 month ago, in which we also observe the nature of this matrix in the meteorite. We were going deep to nanometric scale, using a very high resolution transmission electron microscope that is at Granada University in Andalusia, where you can see here, this is 200 nanometers scale, and you can see here some funny elephant that is produced by phyllosilicates. These are different, you can see identified the different boxes that are in here. Probably you cannot see at this with this screen, but you will see in the PDF. These are the different minerals identified using this transmission electron microscope. The interesting thing of this image, when you compare with the X-ray mappings for each element, is this sulfur, and iron. So you see that they are phases really close by a phyllosilicate that are highly reactive. So in our opinion, if these phyllosilicates are produced by interaction with water, then these highly reactive minerals shouldn't be here. So we particularly think that observation at nanoscale of the matrix of some of these carbonaceous chondrites could be very important to demonstrate if wet accretion was taking place. Wet accretion means that incorporation from the protoplanetary disk of hydrated minerals into the structure of these asteroids. In some cases, for example, this amazing meteorite, we observe these structures that, if you go in detail, is really amazing, the degree of aqueous alteration in which you have the pyrrhotite gone. This hole was pyrrhotite, but under the effect of water was transforming in these magnetic clusters, magnetite, and of course also formation of carbonates sometimes. And we have also discovered, that will be getting out soon in Nature Astronomy, the first piece of a comet, or an object at least, that we have not in our meteorite collections. This is the small cluster you have here, okay, that we have been studying. My PhD student that 1 year ago was doctorated cum laude, Carles Moyano, was just studying in Carnegie Institution in Washington, just in order to study the different chemistry that is hosting this cluster. The amazing thing of this is that you have a carbon-rich class different from the matrix of the meteorite in terms of the carbon abundance. It has mostly normal hydrogen and nitrogen isotopes, but higher presolar grains abundances and what is called glass with embedded metal and sulfides. That this is a typical feature of material that have been subjected to cosmic radiation in the outer space. So we propose that this is a sample, perhaps, of a fragment, a small fragment of a body, and will be a forthcoming paper soon. The amazing thing as well is that we think is also evidence for accretion, wet accretion, in the sense that we see in the border of the cluster that is also enriched in oxygen 16. So it's kind of really beautiful evidence we have just discovered in Barcelona. So I'm very glad about this discovery as well. We have also discovered at UCLA the first flow of water dilution in a carbonaceous chondrite in this MET 01070 that has also extensive aqueous alteration, and is producing this kind of lenses, probably indicating that there is some kind of thermal gradient able to make the water moving through the body, at least up to the point in which no more energy is able to. When this process stacks, then particular aqueously alteration minerals are precipitating from the aqueous fluid, okay, and they are producing this kind of lens features we are observing here. It has also very, you can see here, phosphorus, nickel, sulfur, also very interesting elements from the point of view of origin of life. And one of the big issues about the origin of life are also related with the origin of phosphorus. Just keep this in mind, because we have also interesting results coming soon, hopefully, on this issue. And I want to particularly focus, because I think it's absolutely relevant, the importance of aqueous alteration in these asteroids. There is isotopic dating of the carbonates This was made first, to my knowledge, by teams of Japanese colleagues, are really good with tiny things, and then they were able to get carbonates dating in some of these carbonaceous chondrites. And they realized that these carbonates were produced during the first 10 millions of years of the history of the parent asteroid. This means that these asteroids were soaked in water many tens of millions of years before of the formation of the Earth. And this means that most of these soluble organics that are discovered in Murchison or in this fascinating meteorite that has an order of magnitude higher abundance in amino acids than Murchison, all these were produced by interaction of water with the minerals. And in fact, this was the point that was promoting us to make some laboratory experiments. And here is described the procedure, but of course you can go to the paper in detail. And we were analyzing the catalytic effect of 6 carbonaceous chondrites that we pick up quite randomly from the NASA Antarctic collection. They were just sent from the Johnson Space Center to the Institute of Space Sciences. We just ground 50 milligrams of the stone in agate mortar, and then we brought the samples to Italy, where the team of Professor Raffaele Saladino was doing some of these experiments, in which you see we have different scenarios with thermal water and seawater in presence of the carbonaceous chondrite powders, and without, as a blank, you know. This is the way in which the organics were analyzed. And to identify the structure of the products, 2 strategies were followed, using the spectra compared with commercially available electron mass libraries, and this analysis by mass spectrometry with standard compounds. And what we found? We found that in presence of formamide with hot water and the meteorite powders, no other thing, you can generate almost everything in the prebiotic, you know, scenario. All these amino acids, nucleobases, analogs, miscellanea. So these are the experimental conditions. 1% of the meteorite, 59% of formamide, 40% of water. The temperature was 140 degrees Celsius, 24 hours. And we got all this. So, of course, this has changed completely our minds. Initially, I was thinking, okay, this should be produced at some point in the parent asteroids, because in the right conditions they reach the Earth, and they were just providing a very good setting, you know, to promote chemical complexity. Well, the thing is that we have evidence of this late heavy bombardment, this change, this cataclysmic event that was going all over the solar system. We know that the migration of giant planets are not exclusive of the solar system. We are observing also in other planetary systems. So is a clear example that all these materials form in the other part of the protoplanetary of the main belt. The main belt in the past probably was 100 times or 1,000 times more populated than nowadays. And most of these bodies that were condensing and were aggregating in there were scattered gravitationally because of the migration of Jupiter and Saturn. At 3.8, 3.9 million years ago, these were falling against the Earth-Moon system, as we have from the lunar rocks, all this dating of the big basins and big craters on the Moon. And at the same time, for sure, these were scattered all over the solar system. And of course, if you have Jupiter and Saturn being the main, bodies promoting all these cataclysms, then you have these planetary bodies, the satellites of Jupiter and Saturn, that perhaps have also received part of these materials. I will go over this later, but I think the most amazing thing of these experiments that we have demonstrated that the minerals forming carbonaceous chondrites have catalytic properties that we don't know in any other rock, neither in Earth, Mars, Vesta, or whatever. And we need to keep exploring this in order to see if this is a really good scenario to understand the increasing of chemical complexity. We are very far away from now about the origin of life, but a first step to make the appearance of life likely than we expected. I want also to focus in another important thing, in my opinion. You probably know about the enantiomeric excesses. Some organic molecules exhibit chiral structures, the right and left hands. You know that the enantiomer is one of two stereoisomers that are mirror images of each other. Okay? And in Earth, only the left forms, the Lavoisier forms, are viable for proteins and enzymes. Well, Cronin and Pisarello were found that the Murchison and other carbonaceous chondrites have enantiomeric excesses in amino acids similar to terrestrial. What is this saying? Well, this is saying that somehow this happened. We have no idea how this happened. In nature, in the Earth, we have that the L forms for proteins and enzymes are dominating. To my knowledge, but perhaps Muriel can give me many other light, to my knowledge, the likely way to do that is that you originally, in a natural way, you have, if this carbonaceous chondrite were playing a role and, let's say, bringing these materials to the surface of the Earth, and the minerals, in case that more of these organics were not able to, were destroyed during vaporization and so on. We have, on the other hand, laboratory studies that say that it's not complete the vaporization of these materials, but in any case, just in case that the minerals arrive there and they have some role in producing complexity, these left forms probably are inherited of the carbonaceous materials that were forming these asteroids. It's interesting somehow. Of course, if we are looking to the oxygen isotopes, this was a very famous work by Donald Clayton, 1973, where they developed this delta 18 oxygen, which you can apply to any of these isotopes, but here we compare the ratio of oxygen 1816 from the sample to the oxygen 1816 of the standard mean ocean water. We can compare this ratio with the water on the ocean, okay, of the Earth. This is less 1, and this is multiplied by factor of 1000, okay? And if we plot this in here for delta oxygen 18 and delta oxygen 17, we see that there is a line in which all terrestrial rocks are, more or less, could be some scattering, is the terrestrial fractionation line. And look at that, we have the enstatite chondrites in here. And in here we have the ordinary chondrites of the high FeO, you know, rich in iron or low in iron. And we have here the sea ice, Ibuna-like group of carbonaceous chondrites. And these are aligned. On the other hand, we have the COs, carbonaceous chondrites, CKs, CBs. This is the line of anhydrous carbonaceous chondrites that is quite different slope from the terrestrial fractionation line. What is this meaning? Well, this is meaning from the point of view of the right mixture, and we were just talking before. Probably most of the materials forming the Earth were from bodies that were having this type of composition. Of course, was a big mixture, so for sure some carbonaceous materials also reached the Earth and were forming, but the dominant part of the Earth was mostly by this type of ordinary chondrites. On the other hand, we also, when we compare with other observations, these are the osmium 187-188 ratio, and you compare the carbonaceous, ordinary, and enstatite, you see that the primitive upper mantle of the Earth is releasing, you know, this osmium in some values that are similar to the ordinary chondrites. So this is also bidding for a significant contribution of these ordinary chondrites to the mixture. So in order just to fix some ideas, let's see how is formed comet Will 2. And this has been achieved thanks that in the Stardust mission, from which some of us were participating in the preliminary examination team, were able to collect, this is the aerogel, silicon dioxide aerogel, in few millimeters the particles penetrating in here. This is the top of the aerogel, this is a cut, sectional cut. You see that they are bulbs just created by the, the vapor phase in which part of the materials are vaporized at the penetrating. Part of the wall are covered by these fine-grained materials, but at the end you have these tiny things that are mineral grains in comet Will 2. The amazing thing of the aerogel, this technique, is that the sample collector was exposed during some time with particles that were released from the comet and just were colliding with the aerogel, with also the aluminum foil that was used to fix the aerogel itself. Well, these particles, what are the composition of these particles? This is just an example. I cannot go in full detail, of course. This will require many of these talks. But the largest recovered grains are having diameters between 5 and 15 microns. The toughest fragments you see were captured are mainly made by olivine and pyroxene, and in some cases you have these ending particles and this is a nice example. This is the Febo particle that we were studying, and particularly that Gabriela Matag was studying with the high resolution transmission electron microscopy, was studying this part in here. The funny thing of this particle is just you have this troilite mineral grain that was in front of the particle, so it was shielding the fine-grained materials that were behind. It preserved of this material of become fragmented and just going through the walls very quickly. Okay? You have also a enstatite grain in here, so enstatite is also forming comets. And the amazing thing of this is that this is fine-grained solar composition material, that when you look in particular to this area, you find in here a nitrogen 15 hotspot, as you expect to have in materials that are coming from interstellar space. So the amazing thing of this particle is that you have minerals formed at high temperature, so in the interior of the protoplanetary disk, together with materials that were condensing in the outer space. So comets are a mixture of fine-grained materials coming from many places in the protoplanetary disk. If we look also to the deuterium ratios, many times, well, in the news you can hear everything. Well, it's clearly demonstrated that the water in the ocean is not coming from comets, because some guys have been observing that most of these, highly eccentric comets are not having deuterium hydrogen ratios, and blah, blah, blah. But don't forget, we are missing part of the movie. We are missing the movie in which you have transitional bodies in the other part of the main belt, like Hartley 2, Will 2, okay, that are having similar deuterium hydrogen ratios. So perhaps the bodies that were bringing most of the water of the Earth are not so common at current time, but were part of the bodies that were scattered all over the solar system at the time that happened, probably, the migration of the Jupiter and Saturn, the giant planets. So this has very deep implications, of course, on the future of many of these bodies. And I am afraid that I will go a little bit fast now, but of course you can imagine that we have now some idea of the origin of water, of the origin of deuterium, these kind of things. And I want to go quite quickly about chondrites. The word chondrite means that has no chondrules. The materials have been, they are igneous meteorites. They are segregated from the primordial materials, from the chondritic materials, were melt and were some secondary minerals produced by the igneous processing of their parent big asteroids or even planetary bodies. A clear example is Vesta. I brought with me a thin section of this meteorite, Puerto Lápice, that we recovered in Ciudad Real in Spain, 2007. It's a piece of asteroid Vesta. And then, or some of the pieces that are scattered in the solar system from this asteroid, because I will explain you later. And you have also the chondrites diversity. The primitive chondrites like Acalpucoited, this one, Lodranites, Winonites, the asteroidal chondrites, there are many types in here. In between you have the basaltic asteroidal chondrites that are the Howardites eucrites and diogenites, the HED echondrites that are coming likely from Vesta. And when we have also lunar echondrites and Martian echondrites that are known by the three meteorite types: Cercotites from Cergoti, Nuclides from Nucla, Chassinite from Chassini. Well, of course, as these are igneous meteorites that are produced from chondrites thermal processing, you can have different compositions and a big variety of bodies. Some of these meteorites I'm showing you form part of our meteorite collection at the Institute of Space Sciences. This is a very beautiful, see, some regolith, clearly with different clasts of different lithologies. This is a famous Peña Blanca Springs Albright fall. And in general, you can find that some of these echondrites are coming from many bodies in the solar system that we still have not explored. So in general, we have no clear idea what are the progenitors. Fortunately, we have falls like Almahata Sita. That was, I remember you that this was the first fall of a near-Earth asteroid discovered 20 hours before impacting the desert of Nubia in Sudan, in 2008. This was studied by Peter Jenniskens from NASA Ames. A very amazing discovery is that this was a complex mixing of different types of materials, even some kind of new unknown materials, chondritic materials, and were collected all over the desert of Nubia, and then, as you can imagine, provide a lot of information about different bodies in the solar system. Many of these meter-sized bodies that are going through the Earth space can be also produced by different lithologies and are consequence of continuous collision between bodies, or they can be coming from the surface of bodies that have been affected by impacts over time. Then we have the Howardite eucrite diogenites from Vesta, but still they are another basaltic meteorites that are exactly not the composition of Vesta or the Vestoids, that are the fragments of Vesta, like for example Magnesia. That is another type of basaltic body. And of course the new missions are able to go in full details to explore the structures, the surface of these bodies, and learn many things on that. Then we have the lunar echondrites, and of course the lunar rocks, more than 400 kilograms or almost 400 kilograms of lunar rocks brought by the Apollo astronauts to Earth that allow us to add real science dating of the surface of the moon that can be added to all these crater counting measurements about the ages of some of the lunar surfaces. We are also studying in our institute the reflectance properties of some of these lunar meteorites. This is one example in which we compare in here, this is a Howardite from Vesta, this is Puerto Lápice eucrite from Vesta as well, and this is a lunar where you can see here, the elbow in here is deeper. That is a consequence of this fine grain regolith that is forming this lunar breccia. We are also studying Mars, particularly studying Martian meteorites, the Sergotite, Nuclide, and Chassinite echondrites. We know so far 227 Martian meteorites, and they can be distinguished by the aluminum silicon magnesium silicon ratios that are distinctive of the Martian meteorites compared with the Earth ones. Okay, and the demonstration that these meteorites are from Mars, as you can understand, was long debated, but came from the study of the trapped atmosphere in one Sergotite. In the Sergotite glass is trapped the abundance of the main components of Martian atmosphere. This was an important result by Bogart and Johnson in 1983, and from them is clearly demonstrated that these echondrites are coming from Mars. Meteorites that were formed at different times when Mars was absolutely different to our present time. This is a work by a colleague of the Centro de Astrobiología in Madrid, Fernández Remolar, in which they were just proposing a very different climatic environment in which liquid water was present on this surface of Mars. On the other hand, from images from Mars Global Surveyor, for example, we have all this evidence for floods and even formation of river structures in the surface of Mars. So water was at different times quite abundant in the surface of water, in the surface of Mars. And even nowadays, the new exposed craters by quite recent impacts are exposing the permafrost inner layers that is clear evidence for water behind meters or tens of meters below the surface of Mars at current time. So even Mars Global Surveyor observations of the borders of some of the craters reveal the presence of this kind of structures that are changing over time, and is evidence for salty light kind of streams that are able to be released from the deep part of the surface of Mars. So this is really suggesting that water is very abundant in Mars. You know also the recent discovery in the south pole of Mars of a lake in depth. So this is really making Mars a wonderful exploration goal for the future missions. And in fact, we are now also studying some of these primitive echondrites like Alan Hill's 8401. We were particularly studying, here it's not very easy to see, but these are some carbonate globules that you can see here with different layers. And what we discovered is that the carbonate globules were accreting in different stages with different chemistry. And this means that when this orthopyroxenite, this particular meteorite, was forming part of the surface of the Mars, was soaked by water in different times, and as a consequence of different elemental dissolutions, was able to precipitate and growing little by little with different chemistry. So this is also pointing that 4 gigayears ago in the surface of Mars we have also water in significant abundance to produce all this fascinating chemistry in the interior of meteorites. I put here some slides, just comparing some of the different meteorites from Mars we know with the recent studies by the pathfinders. I will skip this for just matching the time. Then we have the stony iron meteorites, in which you have this metal with silicates like pallasites, so fascinating meteorites with the specific oxygen ratios that are just allowing us to see what is the relation between these metal meteorites. The fascinating thing of these stony irons and the iron meteorites, that when you have iron meteorite that is relatively easy to buy, in the some meteorite shops, you have a piece of a planetary body. You have in your hands a clear proof that planetary bodies were disrupted in huge collisions over time, and you are just getting a piece of a core or a mantle when you have a pallasite in your hands. So fascinating. And just to end, a little bit about giant planets, concerning these so different planets to the terrestrial ones. You have gas-rich planets, particularly hydrogen and helium, Jupiter and Saturn, and Uranus and Neptune, more ice-rich planets. How they were formed? We think perhaps some kind of mixing models could be the best way to understand this, probably by fast accumulation of many of these cometesimals, so with getting some big cores over time, but also probably, as particularly Jupiter and Saturn, that were formed very quickly, probably just were having, they grew from the gravitational instabilities in the disk, as Professor Maynet was also suggesting this morning. So, in general, we have that these giants were the first planets in our solar system, and as I explained you, they probably had a very important role in the evolution of the solar system. But these planets by themselves contain planetary bodies, the satellites. And remember for the future that some of these satellites were oceanic walls. Good example, in the Galilean satellites, Io is too close, is too affected by gravitational, tidal effects of Jupiter, but Europa, Ganymedes and Callisto probably were oceanic walls, were covered by water. In the same time, there is clear evidence. We have space mission of NASA going to Europa, and there is clear evidence for water in the interior of Europa. And again, if we look at the largest satellites, particularly in Saturn, with Titan, with all this complex chemistry of the overdense Titan atmosphere, we really realize how important was also the arrival of volatiles to these planetary bodies. And I just bring you some other question to think about it. When we compare Titan versus Earth, we realize with the deuterium, hydrogen, carbon-12, carbon-13, and nitrogen-14, nitrogen-15, oxygen-16 to 18. You see, this is the comparison with the ratios in the atmosphere of the Earth, and you see that is a very good match. This can be a consequence of irradiation, but if we look to the molecular nitrogen, it's still close to the values in Earth's atmosphere. And what does this mean? well, somehow perhaps we have that the origin of the volatiles in the planetary bodies surrounding Jupiter and Saturn it was the same origin than in Earth and Mars and other planets. So they were consequence of this scattering of volatile rich objects over time. And of course we still have a lot track to go, and that's the last slide with the recent studies of the Pluto system, you know, by New Horizons, also suggesting that these bodies could have been oceanic in the past. So this brings us many other astrobiological fascinating places to visit in our own solar system. So thank you very much for your attention.